In this video, I want to talk about some concepts related to pKa and pKb. And there's nothing mysterious about this letter P. It's the same thing as the P and pH. So I'm going to use an example of an acid. So I'm going to use acetic acid, which has a methyl group, and then the carboxylic acid group. Of all these four protons, only this one breaks off as H+. So just make sure you understand that in organic compounds, only acidic hydrogens are these carboxylic acid groups. When combined with water as a reactant, there will be an equilibrium between protonated water. So the acetic acid has transferred this proton over to here to form H3O plus hydronium, plus whatever's left over after the H plus leaves. And what's left after the H plus leaves is acetate. The naming conventions of the acids follow the ic acid. The anion, which is conjugate to it, is the 8. All right, so this is the acid, then water, and then H3O plus, and this is the conjugate base. Okay, now the equilibrium constant for this is given by the symbol Ka. So this is the acid ionization constant because you start with an acid and you get ions, one of which is H3O plus. So any reaction where you have an acid, no matter what it is, plus water gives H3O plus the conjugate base is going to have a equilibrium constant denoted by Ka. No other reactants or types of products. You have to have H3O plus, you have to have water as the other two parts. And for acetic acid, the numerical value of this equilibrium constant is 1.8 times 10 to the minus 5. pKa is just minus log of that, and you calculate it just like you would pH. I almost wrote pH. 4.75. Again, it's the negative of the logarithm. So that's pKa of acetic acid. Okay, that's all very clear, I hope. Now let's look at another example of something reacting with water, but this time it will be a base. So I'm going to use this molecule, actually an ion. It should look very familiar because we just got it. And so this will be a base. Then, of course, the other reactant will be water. And then an equilibrium with hydroxide. And the conjugate acid, which is acetic acid. So basically, these two reactions, one is more or less the reverse of the other. It's not quite true because you can see one reaction has H3O plus, the other has hydroxide, and they're on different sides. But the conjugate base, so it's a conjugate pair. So conjugate doesn't mean weaker or less than, because this is acetic acid, the very same acid, the thing we just called a normal acid. So we just label it conjugate if it comes as the product of something else that's related as a conjugate base. All right, now this has an equilibrium constant called Kb. All reactions that have some base and water as the two reactants and hydroxide as one of the products and then the conjugate acid, that equilibrium constant has a special name, Kb. It turns out that that is 5.6 times 10 to the minus 10. All right, and so pKb is 9.25. Now there's a relationship between pKa and pKb, much like there was between pH and pOH. And that is that they add to 14, which means their product is 1 times 10 to the minus 14, the kW of water. And to see why this must be so, is we're actually going to add these two reactions. Remember, when you add two chemical reactions, you multiply the equilibrium constants. So, when we add these two together, the acid and the acid, they're on both sides of the equation, they cancel. The base and the base are on opposite sides and they cancel. And the only thing that does not cancel is 2 water H3O plus and hydroxide. This is the equation for Kw. And since this reaction K must be the product of these two Ks, this K is Ka, this is Kb, then Kw must equal to Ka times Kb. So what we're going to do is actually utilize this equation, because it turns out that when we look for acetate Kb, we're not going to find it. You're supposed to know that if you can't find Kb of a base, try to look for the Ka of the conjugate acid. If you can find it, then calculate the Kb from this little equation. The other thing that this equation kind of makes sure that you need to understand is that since this product of these two numbers is a constant, the larger this is, the stronger the acid, then the smaller this number has to be, and therefore the weaker the conjugate base. So there's an inverse relationship between the strength of one of the pair and the weakness of the other. Now generally when we say weak acid, there will also be a weak conjugate base. In the very extreme cases where we have a strong acid like HCl, the conjugate base is chloride. It's so weak we just consider it to be neutral. And so you actually have to know what the strong acids are, and that'll be the topic of the next video. There you go. That went pretty well. I almost did everything I wanted. That's good enough.
Get a space?
Yeah.